Hi everyone, welcome back, and today we're going to be talking about processes. So first, let's start with a definition. What is a process? Well, a process is just a running program, a program in the middle of execution. And one problem that you might run into, well, you probably won't because consumer devices these days typically have CPUs with many cores on them, but a problem that was very important in the early ages of computing was, what if we have many programs but only one CPU to run them on? What do we do? And some early approaches to this were to simply do batch processing, so running all the programs in sequence, or buying more cores, simply buying more CPU cores. That can be expensive though. And distributed programming, doing networking to distribute the work of a program across multiple devices. Now all these operations they're somewhat effective, but they're not as nice as the approach that most consumer devices use today, which is time sharing. So time sharing is the process by which the CPU or the operating system virtualizes the CPU, giving each program running on it the illusion that they have their own CPU that they're running on. And the way this works is the CPU basically schedules tasks, schedules processes to run at certain times, and it has the ability to stop a process, pause it, and let another process run when necessary. This could be when you interact with the process, for example. If you have multiple browser tabs open, when you open up one tab, that tab now has the ability to run and has access to the CPU. This was a really big thing in the 70s when CPUs or computers before that didn't really have the idea of time sharing. When the time sharing was invented, it allowed thousands of people potentially to all use one device at once. That's really cool. Can you imagine going to a university like UCF and there being one supercomputer there, one server, let's say, but only one person was allowed to use it, or a handful of people were allowed to log on at a time. And then suddenly, after time sharing was invented, hundreds of students, thousands of students were allowed to log on to that device at once. This is why we're able to all use Eustace at UCF at the same time. The way the operating system actually manages this, pausing and resuming of programs, is through this idea of a process control block. Now, this isn't an actual structure in the kernel. There is no struct in the C code defining the kernel for a process control block, but the process control block is sort of an abstract concept defining what the kernel saves when it pauses a process. This includes things like the process's ID, the values in the registers as the process was running, the current working directory, and all the other things listed here. You can find out more information about this, I'm going to change tabs here, by looking at the man pages for procfs. This tells you more information about processes on your Linux distribution. If you ever want to search the man pages for more information, by the way, you can use the apropos command and pass it a string of what you want to search for. So if I search for process information, you'll see that several results are returned, and these all probably give me more information about how processes work, but the one that I'm pointing out for this course is just procfs. Okay. So how are processes made? Well, processes, they are made by duplication. So think of like a cell duplicating itself. Each process, when it duplicates itself, its duplicate is called the child process. And the child process is the exact same as the parent process. This duplication happens by a call to the syscall fork. And so you might be wondering, okay, if a process can only create more processes by duplicating itself, how do we have different kinds of processes on the machine? Well, that's with this next syscall exec. So exec replaces a currently running process with a new process. It does not create a new process, I should say, it just replaces the currently running process with a different program. So it's very typical in systems programming, especially in C programming, to see this sort of fork exec pattern where you fork a process, and then in the child process you exec a new program to replace the child with whatever program you wanted to run instead. And the next question you might be wondering is, well, okay, if all the processes are made by duplication, where's the first process? Because if we start with 0 processes and duplicate that, we still would have 0. So how do we actually obtain processes on a machine? And the way this works is through the program called init. And there's different kinds of init programs on different machines. One called sysv used to be fairly popular, and there are other variants, but the one that's sort of won out and become dominant these days is systemd. And you can actually open the man pages for systemd on your machine. It's the systemd System and Service Manager. You can read more about it here. In fact, if I actually type in init, it'll bring me back to systemd as well. And you can see that systemd actually starts with PID1. So the init process has PID1. One thing I'll note here is that systemd actually, when it started to become popular, it was a bit controversial. So systemd is actually a fairly new program in terms of the Linux world. It was developed in 2010 by Red Hat, and it's become a little controversial because some people accuse it of being a very bloated piece of software, doing more work than it needs to do. Other people say that its dominance has encouraged homogeneity or sameness across Linux devices, which is sort of antithetical to the Unix way of having specialized tools for each job and specialized distributions that are all unique. But in any case, regardless of your feelings, systemd is sort of the dominant init program these days. And once systemd runs, it actually starts forking off into other processes. And you can view these processes with this syscall ps. So if I run ps, you can see some processes are here. Now, these aren't going to be many processes because they only show processes owned by me, and they only show processes that were made by interacting with the bash shell that I'm running by default. I can add all the processes from all users by typing PSA. You can see more users appear, but this still isn't exactly useful to me. I could add U to see the names of the users that ran these processes, and you can see here, along with some more information, you can see here the root user is the one that started these two processes with the PID 1962. And if I wanted to view processes, including those that were not started by the shell, that are not tied to a interactive shell, I can put the X flag here. And you'll see we get many more processes this way. Another thing I can do is use the J flag, and what the J flag will do is print out a job-oriented output. This is not really relevant to us right now, but when we get into job management later in this course, this will make more sense. And finally, you can also use the F flag to print out forest output. And what that means is that it's a tree-like output here. So you can actually see that it uses a little bit of ASCII art to depict that this PS command that I just ran branches off of the bash command. You can also see the arguments here. But there's actually a better way to obtain tree output, and that's to use the ps tree command. So if I run ps tree here, you can see a nice Unicode character depiction of the tree that is formed from the init program, systemd, up here. Now, we can view more if we use the -a flag. We can actually see processes that only belong to a certain user. So, by the way, this user variable here, it just expands to my username. And on my machine, that's bpapis for brunpapis. So if I type this in, you'll get the same results. But for you, if you're on Eustace, you can actually run this command. And you want to use $user, it will just expand to your NID on Eustace. And what we can also do is specify only the processes that come from that are the children of another process. So if I do $, that actually expands to the ID of the current process that I am running. So I can maybe do echo to show you this. Echo prints whatever you pass to it. If I pass this here, you'll see that I have PID 26758. And I could actually run PS, and you can see that my bash process actually has the same PID 26758. So if I do PS tree -a $, I will only see the commands that stem from or were originally forked from my bash process. So I hope the idea of processes forming a hierarchy is starting to come together for you. You might recognize that this is similar to the idea of file systems forming a hierarchy. And I think that just should be interesting to you that these two hierarchies are both interacting. The next topic I want to cover is standard I/O. And you might have a question, you might be wondering, where exactly does printf's output go? And you probably know the answer to this, but it goes to the terminal. And that's because of this implementation of printf here. You can see we are calling vprintf and passing standard out as the output to it. But what if we wanted to change the output of our program? We would have to modify the source code itself to write to a file or to a network socket or to some other kind of file-like object. And that would be annoying, so Unix actually provides us with this convenience of file descriptors. And it gives us 3 file descriptors whenever we run a program. So standard in, standard out, and standard error. Standard in, let's see if we can see some examples here. Standard in is the input you type in the terminal. We'll see examples shortly. Standard out is what is written to the terminal, and standard error is another string that you also see in the terminal, but can be redirected separately from standard out. And why would we want to do this? Well, you might have a program that crashes and you want to see the error log somewhere, or you might only want to operate on a program's normal output and ignore its error output or debug output when you're doing some text processing on the program's output. So it's useful to divide these two. So if we run this command, hello world, in bash, hello world, you can see it gets printed to standard out because it's on the terminal. And where does standard in come from? Well, it comes from what you type in on the terminal. So if I type in cat, or let's see here, I have some files in this directory. This file, hello there, hello.txt. Let's look at hello.txt. I'll just put hello inside this file. If I pass this file to cat, it will print out the contents of that file. But if I don't type a file name and just type cat and press enter, cat will await me to enter input. So I will start typing in something here. I'll say hello world, and you'll notice that as I'm typing, cat is printing back out what I've typed in. I can end this by pressing Control D, and that will signal the end of input, and cat will cease. There's another program we can use called grep. Grep is very useful in that if you pass it a string and then the name of a file, it will actually print out any matches of that string. So if I go into that hello.txt program here and I add more contents, goodbye, so long, hi, bye, and then hello again at the end, and then I run grep on this as before, you can see it prints out all the matches. But grep too, just like cat, enables you to enter input from the command line. So if I just type in grep hello and then say hi, bye, hello, you'll notice that grep will only respond and print something out when I type in hello, and it'll print it out with this nice color formatting here. So I'll terminate this with Control D, just as before. Let's return to the slides. And running programs, we've seen this before. Just type the name of the program and press enter. So I'm not going to show this, but you can just get all the list of files in your current directory by running ls. There's also command line arguments, and there's a few different ways to get this. If you're writing a bash program, I believe there is a bash built-in called getOpts, which lets you get command line arguments. But in this course, we're working in C, and there's actually a library called getopt. So it's singular, getopt, not getOpts like the bash command. But the C library getopt will be useful for you in the next project called myfind, so we'll be using it there. And you can read the documentation here in the man pages. It essentially enables you to more easily parse arguments from the command line in your C code. Here's an example of passing arguments to ls, which is likely implemented using getopt. Now your next question might be, where are my programs? So you might have been wondering, I think we've seen this variable before, path. Let me echo it out so you can see what its contents are. So we could use echo, but I'm also going to show you the printenv command, which lets you print environment variables directly by name. So if I just type in path, you can see the contents of my path. Now what is this? Well, the path is a sequence of colon-separated paths to directories. You can see, ideally to directories. I think you can put files in here as well, but you'd only want to use directories in practice. Each one of these colons separates a unique path, and what this will do, how the path influences your operating system, your program execution, is that when you run a program like ls, let me actually print the path out again. What your operating system, or your shell, will do, I should say, is search all these directories for the program named ls. And once it finds that program, it will stop, run it, and it will not continue searching for another program named ls. So in my case, it should stop right here, I think. User bin is where ls is. And we can check this by running the which program. So which ls will tell me the first match of ls in my path. So you can see here, user bin ls, that's exactly what we found. If there's multiple matches, you can type which a to see them all. You can look at the man pages for which, and it will actually tell you it does this searching the path for executable files matching the names of the arguments. So you can always use, so the output of which will actually tell you where in your path, which path first contains an executable that you pass to which. But some programs may not be in your path. So let me make a program here, call main.c. Actually, let me call it hello.c. Hello.c. I have a macro in vim here, so it's going to autocomplete the program for me when I press space. Okay, I'll just save that. And if I make this program with GCC, hello, and hello.c, then I can run this program with /hello. But why can't I just run hello and run this program? You'll see I get a warning here telling me that hello is not found. Why is this? Well, it's because the program is not in my path. As we just said, the bash, the shell, will search your path for executable programs by name if you don't enter a full path to an executable. Now, one reason why you'd want to have this sort of like requirement of specifying paths to run executables in your current directory is for security reasons. You don't want users to accidentally run a program they didn't intend to run. So it has to be either in their path, or it has to be, or you have to specify the path fully yourself. Now, some commands aren't actually programs. So if I were to do which for cd, you'll notice that I get no output. Instead, this is a shell built in, and the way we can check that is by using the type command. And you can see that it says cd is a shell built-in. You can always check what a program is by using type. So if I do type find, it will say find is hashed as user bin find, so find is user bin find. You can ignore the hashing part, but it is user bin find, so it's not a shell command. And some commands are actually both. So if I were to do type echo, you'll see that it says echo is a shell built-in, but if I add the -a flag here to show all results, we'll see that echo is not just a shell built-in, but it's also found in these locations as programs. And just like which, the first result the type shows is the one that actually gets executed by your shell. So the shell built-in overrides or supersedes the the program called echo in user bin. So a quick quiz: how do I run a program that I name cd, assuming it's in the current directory? Well, the way to do that, you would just specify the full path cd, like we did with hello. But how do I run echo, assuming it's on my path and a shell built-in? So how would I run the echo program, not the echo built-in? Well, if I were to run echo hi, I'm actually running the shell built-in. The way I can get around this is by specifying the full path to echo. And now I'm running the echo program installed on my machine. But there's another way as well that is a little more esoteric, but it's a bit more concise actually. You can use the command. This is also a shell built-in, but what command will do is it will skip looking for a shell built-in and use a program on your path instead if it finds one. So if I do command echo hi, I'll be using the shell built-in, or the program for echo here instead. You can also reverse this by using the built-in command to use the built-in instead. And if command does not find a shell built-in for a program, like find, it will default to using the, or I'm sorry, like cd, it will default to using the shell built-in. So that will still work. Now for redirection, so we can actually change in bash where our programs read from and what they write to. So to give an example of this, we can change our redirection, or some categories of this before examples. We can use the less than sign here to read from a file, change standard in, the greater than sign to change standard out, and the to greater than sign to change the standard error output. We can also use the double tags here to append to a file. So if I were to, let's say, open a file here, let me count out the contents of hello.txt. You can see we have these words in here. If I did ls and ran and did double greater than signs to hello.txt, and then cat out the contents of hello, oops, you'll see that now we have the contents of this directory in here as well. There's also here documents, which are a neat trick. The way here documents work, I'm going to paste this one in here. You use double less than signs instead of greater than signs, less than signs, and then a special sentinel string. So this does not have to be EOT. It can be whatever you want. I'm going to change it right now to EOF. And you can type in whatever you want afterwards. Multi-line strings are allowed, and when you press enter, assuming that your here doc correctly ends with the exact string you typed in, no spaces or anything, just the exact string you typed in at the beginning of the here doc, it will actually run the program you passed to it with that string you passed, the here doc string, as standard in. This is cool because you can actually place shell variables in here. So if I were to go back, let's go back to right here and type in my name, the shell variable user, so my username, and let's run cat instead of grep so we actually see everything we typed in. You can see that this user variable was expanded to be Pappas. So let's see an example of input redirection. So cat, we can pass a file directly, hello.c, but we can also redirect standard in to be hello.c. And this works the same because remember, if you don't type any arguments to cat, it just reads from standard in. So we're essentially just doing the same thing, but by changing standard in to be hello.c instead of opening the file. Now with grep, we can actually read from a file, a header file in our user include directory. So you can find all the matches to the defined search string here. You can combine these too. So we can grep standard.io user include stud.io.h and then redirect the results here to grep results. And now if I were to do run less on grep results, you can see we have all the matches we found earlier just in this file instead of on the command line. So for error messages, if I try to grep for the keyword define in the root directory, I will get an error message because I lack privileges to do that. So bash prints out an error message here, but grep also prints an error message. And if I were to cat out the contents of grep results, you'll see that I think nothing gets executed here. So I think because there's no output from grep, because permission is denied, this command's not even running, essentially. Sorry, this command's not even running because bash does not have the permissions to do this. So we get an error message instead. But if I were to do this, redirect the standard error to grep error, let's see if this actually works. So if I cat out grep error, well, grep error isn't me because the shell is preventing me from running this command. To give you a better example, so these slides were not invented by me, so I'm kind of Unfortunately, I had not prepared for this, but let me give you an example. If I were to try and run cd to a path that does not exist, so I'll say foo, you'll see we get an error message. But if I redirect the standard error to cd error, and then count out the contents of cd error, you can see the error message was redirected to standard error. We can also redirect the outputs to one file. So if I were to try and grep for the defined keyword in the root directory here, which again should give us an error because of me lacking permissions. What this command will do is redirect both standard out and standard error to the same file. So let me see if this works. I don't think it's going to work because unfortunately I don't have sudo privileges with this command. Let me think if I can have a command that prints error messages and regular output. What we could do, I'm going to do this as an example. Let's modify our C program. Oops, hello.c. And I'm going to use fprintf instead. Print this message to standard out. Print this one to standard error. And we'll just say error message. All right. Now if I run this program, you'll see we get two messages, is what it seems like. Hello world and error message. But hello world is actually to standard out, and error message is to standard error. So how can we actually check this? Well, we can redirect standard out to hello dot, or we can just say hello out. Let's say hello dot out. And then we can use the 2 to redirect this to hello dot error. And now if I count out the contents of hello dot out, you can see we have hello world and hello dot error. Oops, error has error message. And what I was trying to show earlier, but failed because I don't have a good that example was not great, I can use this syntax here to redirect standard error to the same place that standard out is going to. So if I run this and then count out the contents of hello.out, we get both messages here. And note that redirection overwrites files by default. So don't redirect to a file if you want to keep your contents. You'll have to use double greater than symbols to achieve that. One other thing to note here is that the order in which you place this redirect from standard error is important. So if I were to place this over here before the redirect to standard out, you'll notice that the error message still appears in the terminal. That's because this redirection to standard out occurs sequentially after the redirect or before the redirect to standard out. So this essentially says redirect standard error to whatever standard out is pointing to right now in this command. So that's why when we ran it this way and then printed out the contents of the message, you can see that it was outputted out here instead to the same file. Okay. So now let's talk about a little bit about pipelines. Pipelines let us connect programs together, and this really adheres to the Unix philosophy. So in the Unix philosophy has these 4 tenets from Doug McIlroy, but there's really 2 that are the most popular. And the first one is that every program should do one thing very well. So you might have noticed that in this course, all the programs we've been looking at so far, echo, ls, cd, cat, find, they each do one rather specific job. And the reason for this is because of the next bullet point here, the next numbered part of the philosophy. We should expect every program, the output of every program to become the input to another as yet unknown program. So it's nice to have programs that are all unique and perform one specific task, because that way you can connect them together into a nice pipeline. If each program is modular, you can construct a nice tool out of stringing them together, connecting them. So to give an example, let's look at find and grep. Find lists each file in a file tree, and grep searches for text. So first let's run find to get all the files in our file tree here, and count out the contents, and redirect it to a file called find results. We can see here all of these. And then what we could do to kind of connect these two programs together is to run grep and then feed it in the results find from that file find results. So what we essentially did was use this find results file as an intermediary, running find to store our find, redirecting our results of find to the find results file, and then reading the contents of that file to grep hello. Now this works, but it's not exactly a pipeline because we have to run two separate commands. What we can do instead is to use a technique called process substitution. So the way this works is we are reading from a file, just like before. We use the same syntax. But now instead of a regular file, we actually are passing a process to read in from. And the syntax for this is very specific. You must use a less than sign, then a parentheses, and then a closing parentheses. And there can't be any spaces between this less than sign and the opening parentheses. And then inside these prepare parentheses, you'll type in the command you want to run. So if I were to run this, you can see we get the same output as we did by running those commands in sequence with that intermediate file. You can actually keep going with this, and let's say we wanted to use the WC command, which prints out the number of lines, words, and bytes in an input. So let me run this again and type in hello there, or hello world, so you can actually see. We had 1 line, 2 words, 12 bytes. So let's say we want to pass the output of this grep hello find redirection that we ran earlier to WC. Well, the way we would do it is to wrap the entire previous command in a process substitution as well. And this way we can actually redirect the outputs of find to grep for hello and then word count. So this works. This accomplishes our goal of connecting these programs together. But there is a better way to do this, and that is through pipes. So let me show you how this would work with pipes. Run this again. We would run find, and then grep hello, and then word count. And now, instead of going from inside out, right to left, we're going left to right, and it's all linear. And you can see we get the same output. So what's going on here is that the shell, what it's doing for you, is keeping find's input to standard in, but changing its output to a pipe, and then grep is reading from that same pipe, changing its standard into that same pipe, and then grep's output is going to another pipe, WC is reading from that same pipe, and then it's writing to standard out, finally. And there's some more examples here. I will skip them. But in the next lecture, we're going to be talking more about what pipes are and how they actually work. So look forward to seeing you then.